In this video, we are going to study properties of Laplace transform. The first property is linearity. So in time domain, we represent linearity as a into x of t plus b into y of t. So here we are adding and scaling two signals. In frequency domain, it will be represented as a into x of s plus b into y of s, and the ROC will be intersection of first ROC with second ROC. Second property is time scaling. It is represented as x of at. In frequency domain, it will be represented as 1 upon mod a x of s by a, and ROC will be in ROC s will be replaced by s by a. So here ROC is going to change in this case. Third property is time shift property. So x of t minus t naught, it is time shifted version of your x of t signal. So if you shift time domain signal in frequency domain, this signal will be multiplied by the shifting factor. So it will be represented as x of s will be multiplied by the exponential term e raised to minus s t naught, where t naught is the shift in the time domain signal. So remember here, whenever it is time shift, we have x of t minus t naught. The same shift, whenever it is negative shift t minus t naught, the power of exponential is also negative, and ROC will not have any change. So ROC will be of your original signal. Similarly, if it is x of t plus t naught, in this case, here exponential power will be e raised to plus s t naught x of s, and ROC will be as it is. There won't be any change in the ROC because we don't have any change in the s of s function of x of s. Next is frequency shift. So whenever it is frequency shift, it will be x of s minus s naught. Whenever we have s minus s naught, in this case, the time domain signal x of t will be multiplied by exponential signal, and now here the sign is opposite of the shift. So here in frequency domain, we have shift x of s minus s naught. Now here exponential will have the positive power, e raised to plus s naught t. Similarly, if the shift is positive, x of s plus s naught, same way we can represent the equation as e raised to minus s naught t into x of t. Now the change in ROC will be, so in initial ROC, the s will be replaced by s minus s naught. Similarly, here s will be replaced by s plus s naught. The next property is time reversal. So if we reverse the signal, so it is folding operation. If it is x of minus t, we get x of minus s. So here ROC will be opposite of the original ROC. So we can say that in ROC you have to replace s with minus s. The next property is conjugation. So if we take conjugate of x of t, in this case we get x star of minus s. So ROC will be again opposite of the original signal. replace s with minus s. Then we have convolution property. So if we have signals x of t convolving with, let's say, y of t, then this convolution in time domain is multiplication in frequency domain. So we need to multiply the Fourier transform of x of s with y of s, and ROC will be intersection of both the signals. So ROC of x intersecting with ROC of y. Next is time differentiation. So if we take derivative of signal x of t, so in generalized term, let us take nth order derivative. So if we take nth order derivative of any signal in frequency domain, it will be s raised to n into x of s, and ROC will be your original ROC without any change. Similarly, we have frequency differentiation. So here this frequency differentiation tells us that if we multiply x of t signal with t raised to n, in that case your frequency represented signal will be minus 1 raised to n d by ds with nth order of x of s. Your ROC will be as it is. And the last is integration property. So if we integrate time domain signal, let's say from minus infinity to t, x of t dt, in this case we are going to divide x of s with s, and your ROC will be as it is. So these are the prominent properties of Laplace transform.